Professor, what did you do to A.B.? I kind of liked him. In a weird way.
I don't know. This is highly irregular.
A.V., are you okay?
Whoa, this is really weird. I must have hit warp speed. I seem to be floating in infinite space. I hope there are no Klingons around here.
Professor Schmohawk, can't you do anything?
Well, I guess I'll have to call Mr. Squidgiopoulos. He's the only one around here who actually knows how this thing works. Hello, Mr. Squidgiopoulos. Can you come down to the lecture hall for a minute? We seem to be having a small problem with the multidimensional conformal space projection configurator. Yes, I know you're very busy. I apologize for the inconvenience. But we may have a serious issue with the configurator. You'll be right down? Thank you so much. Goodbye.
Ah, Professor Schmohawk, what seems to be the problem here?
Oh, Mr. Squidgiopoulos, thank you for coming down. As you can see, we are having a bit of problem with...
Ach, mein Gott in Himmel! This is not good!
Yes, we were hoping maybe you could help us with...
He looks terrible!
Yes, I know he doesn't look very well at the moment.
My poor babies, they have not been feeding you again. Schmohawk, if I told you once, I told you 1,000 times. This is a very expensive equipment, and you must feed the fishy twice each day.
Oh, yes, I forgot.
You cannot forget these things, Schmohawk. This is a delicate scientific apparatus.
But can you help us with one of our students who seems to be undergoing some sort of strange interaction with the configurator? You see, we sent him into a spherically curved three-dimensional manifold, and now he seems to be, well, undergoing some sort of weird distortions.
La 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 la.
Gah! He is hideous!
Actually, that's how he looks normally.
Oh. Now, about the distortions. There's nothing to worry about. Your student is completely unharmed. In fact, he probably doesn't notice that anything is different. Except maybe the strange glow of his own image coming from all the directions.
A.B., don't go into the light!
Don't worry about a thing, young lady. This young man doesn't see himself moving at all. As far as he's concerned, he's always in the center of his unbounded space. And this is similar to the way we see our own universe. We always seem to be in the center, with no boundaries in any direction. But as you can see, this doesn't necessarily mean that the amount of space in our universe is infinite. Our universe may be finite, but curved and unbounded, just like AV's space.
But why does he keep getting all stretched out of shape?
What you are seeing is not AV getting stretched. This is just a distortion caused by the way we are viewing his space. Unfortunately, there's no way to project a curved space like this into our universe without some strange distortions.
Professor! I think Mr. Moose Masher has a question. Professor, what do you mean by distortions? Well, let's think for a minute about the spaces we have created. We started with a two-dimensional cylindrical space.
This is a good example of a two-dimensional space with some of the boundaries removed.
Yes, we started with a rectangular bounded space and then connected the left and right boundaries, so horizontally at least, the space became unbounded. But we needed a third dimension to visualize the left and right boundaries connected together without any discontinuities. A cylinder is a good way to visualize this connection. But, of course, this third dimension did not really exist. It was just a way of visualizing the unbroken connectivity of the two-dimensional space.
But this kind of space is not distorted. All the rules of Euclidean geometry are still valid.
The toroidal space had a more complicated connectivity. It was also a flat rectangular space, but now the left and right boundaries were connected and the top and bottom boundaries were connected. Even using 3 dimensions, there is no way to show the connections for all 4 boundaries without distorting the space in some way. For example, we can start by forming a cylinder to connect 2 of the boundaries. But then we must also connect the other two boundaries. There is no way to do this without distorting some parts of the space. This means that in order to display the space as a torus, the distance between some points must increase while others decrease or stay the same. In other words, the space becomes distorted. But remember that the torus is only a way of visualizing the connectivity of this two-dimensional flat space. If we show the space as a flat rectangle and just remember that the boundaries are connected, then no distortions are needed.
So this space is Euclidean too. Just like the cylindrical space is just flat rectangular space with the boundaries connected differently.
Now, the spherically curved two-dimensional space was an entirely different matter. The distortions in this space were not just as a result of the way that we viewed the space. They were actually inherent in the space itself. This is why we call this space curved. In curved space, not all the laws of Euclidean geometry are valid. Lines that start out as parallel eventually cross. The angles of a triangle add up to more than 180 degrees. The circumference of a circle is not equal to pi times the diameter, and so on. When the space is very large compared to the observer, these distortions are small. If you drew a shape on the surface of the Earth, the laws of Euclidean geometry would seem to hold perfectly well unless the shape you drew was very, very large. This is why it took so long for people to realize that the Earth was not flat.
That's right. If you draw a very small circle on the surface of a sphere, it is pretty much like drawing it on a flat surface. But as you make the radius larger, the geometry becomes more and more non-Euclidean. In fact, once the diameter of the circle has stretched halfway around the sphere, the circle's circumference actually becomes smaller as the radius increases. Eventually, the circle shrinks back to the original size, but now the inside has become the outside and vice versa.
Yes, the same thing will happen with a triangle. Imagine drawing a triangle inside the circle. If the triangle is small, its three angles will add up to about 180 degrees, and it will seem to behave according to the laws of Euclidean geometry. But as the triangle grows, it becomes more distorted. Its angles become larger and larger until the diameter of the circle reaches halfway around the sphere. At that point, each angle is 180 degrees, and the three angles add up to 540 degrees. The triangle now looks just like a circle. As the radius of the circle continues to grow, the lines connecting the three vertices form another triangle. But the inside of this triangle was the outside of the original triangle, and vice versa. The same thing will happen to a square, or any other shape. So on a curved surface, things can sometimes be quite distorted.
But here is the important point. When we try to represent curved space as a flat surface, then we create distortions that are not actually present in this space.
Perhaps an example would help. Let's look at a typical map of the Earth's surface. Now, imagine that you start at the equator and travel towards the North Pole. As you travel north on the flat map, your image becomes more and more distorted. When you reach the North Pole, you encounter what is called a singularity. This is a point where our image becomes infinitely distorted. The North Pole is the entire top boundary of our flat map. In other words, this one singular point on the sphere becomes an infinite number of points on our flat map. Likewise, at the South Pole, you encounter another singularity. This point is the bottom boundary of our flat map. Eventually, if you continue to follow a geodesic path, you will return to your original position and your original shape on the flat map. But remember that these additional distortions only appear when we project the surface of a sphere onto a flat surface. An object moving around in this curved space does not really change its shape as it moves. It only appears to change its shape in our flat representation. So remember, class, on the surface of a sphere there are real distortions because the laws of Euclidean geometry don't hold. And then there are additional distortions caused when we try to map the curved space onto a flat surface. Any questions?
Professor!
Yes, Adrian.
But what about AV?
Oh yes, AV! Maybe Mr. Squeegeopoulos would like to explain what's going on with AV.
What do I look like, Sigmund Freud?
Actually, I meant...
Of course, you want to know why he looks so weird. AV is perfectly hunky-dory. Just like the curved two-dimensional surface of the Earth, his curved three-dimensional space has some small distortions. But the big distortions you are seeing are only due to the way we must visualize his space. Maybe you could understand better if we start with the Earth again and map it a little differently. This time, instead of mapping the surface of the Earth onto a cylinder and then enwrapping the cylinder, let's start by making a small hole in the surface of the Earth at the South Pole. Now, let's stretch the hole bigger and bigger until the entire surface of the Earth becomes a disk. Every point on the surface of the Earth is represented on the disk, just like every point was represented on the rectangular map, but the distortions are much weirder. Now, the South Pole has become the perimeter of the disk, and the North Pole has become a point at the center of the disk. The equator becomes a circle halfway between the North and the South Poles. Now, what would happen as you traveled from the North Pole on a great circle route around the Earth? As you travel south, your image becomes more and more distorted until when you reach the South Pole, your image stretches all the way around the perimeter of the disk. As you leave the South Pole, your image becomes less distorted until you end up back where you started at the North Pole.
Of course! Now I see. This is exactly what is happening to AV, except in 3 dimensions.
Aha! You know, for a PhD college professor guy, you're pretty smart.
Thank you. So you see, class, just like mapping the 2-dimensional curved surface of a sphere onto a 2-dimensional flat disk, the multidimensional conformal space projection configurator maps Mr. Geekman's 3-dimensional spherically curved space into the volume of a 3-dimensional sphere in our uncurved space. Any questions? Okay, when AV appears to be at the center of the sphere, it is just like our example of being at the North Pole on the surface of the Earth. Remember how this mapped to the center of the flat disk? Okay, now when AV floats around to the opposite side of his space, it is just like our example at the South Pole, which was represented by the outer boundary of the disk. This is why his image sometimes stretches around the outer boundary of the sphere. Any questions? Mr. Moose Masher, can AV come home now? Of course. I almost forgot. All I have to do is hit escape. Dang.
Smallhawk, when was the last time you changed the oil in this thing?
There's no place like home. There's no place like home.
Okay, let's fire this baby up again.
Mommy.
Geekman, I never thought I'd be glad to see you again.
Daddy?
Geekman, you're geek meat.
Not Daddy?
Well, I guess that was enough excitement for one lecture. I'll see you all again when we present the next in my series of lectures at... Why You